everyone, welcome to this webinar on Simulx. Geraldine Herral is VP Applications at Lixoft, and she will explain how to define the different elements to set up a simulation from scratch in Simulx. During the presentation, you can type your questions in the Q&A section. We will answer them in the Q&A chat box or orally at the end. The webinar will be recorded, and the recording and the slides will be available on our website by the end of the week. I now give the mic over to Geraldine.
Thank you, Pauline. So welcome to this webinar. As Pauline said, I will really focus on how to set up a simulation in Simulx completely from scratch. So for example, you could have estimated your model with another software. So Simulx is part of the Monolix suite, which also contains pCanalyx for non-compartmental and compartmental analysis, and Monolix for population PK/PD modeling. These three applications are especially powerful when used together, but it is also possible to use them independently. Simulation is our simulation tool, which can be used for decision making. You can start a Simulx project by importing a Monolix run as a basis for your simulations, or by defining everything from scratch. And this is what we will see today. The definition of the scenario is very flexible and intuitive, and you can get all your results in the graphical user interface as plots and tables. If you prefer to script, you can also use the R API. In the exploration mode of Simulx, you can simulate a typical individual and explore in real time the impact of the parameter values or of the treatment. And in the simulation mode of Simulx, you can simulate populations and clinical trials. You can define post-processing of your simulation output into outcomes and endpoints, and even replicate your simulations to assess the uncertainty of the results. Before running a simulation, it is necessary to define the elements of the simulation scenario. So this includes, of course, the model, and also the parameters that can be population or individual parameters, possibly covariates, the treatments to apply to the individuals, what you want to output from the simulation, and the number of individuals. If you import a Monolix project into Simulx, all these elements will be defined automatically, and you can then modify them to simulate new situations. But it is also possible to just define all these elements completely from scratch. For all elements, the graphical user interface really guides you into how to define them, except for the model. So I will put a special emphasis on the model today. To describe the model, we use a dedicated language that is called mlxtran, and that is used in all applications of the Monolix suite. It's a human-readable language with a pretty simple syntax, and it has been designed especially to describe population PK/PD and QSP types of models. We have a very extensive online documentation with many examples, and we also have the MLX editor application, which has a syntax checker so that you can quickly spot mistakes into your model. All right, so this was a quick overview. Now let me introduce the model we will use today. So it's a one compartment model with a linear elimination. I can give the dose either intravenously or it can be an oral dose. And the PK concentration then has an impact on the PD model, which is a turnover model, with the PK concentration having an inhibitory action on the production rate for the response. The parameters of this model have been estimated on a single dose dataset with both healthy individuals and patients. We have inter-individual variability on all parameters except IC50. And it has also been found that the weight had an impact on the volume and on the clearance, and that R0, so the baseline for the response, was different between healthy volunteers and two different types of patients. So that's a model that has been estimated previously, And the goal now is to use Simulx to simulate a multi-dose treatment and assess the benefit of having a loading dose as before the regular treatment, and to check what is going on for the response percent change from baseline. That's really our output of interest for the simulation. To describe such a nonlinear mixed effect model in the mlxtran language, we're going to need different sections into the model. So we're going to have a section to declare the covariates, a section to define the inter-individual variability, and a section for the structural model. And we're going to see how to construct these different sections step by step, starting with the structural model. So the longitudinal section is the only mandatory one, and I will start with this one and then add things on top of it. So to start, I'm gonna open the Simulx application, which is the orange icon. And in the graphical user interface, you can see that I can either import a mlxtran or start completely from scratch. So today I'm starting from scratch. And the first element that I need to define is the model I want to use. And here you can either browse for already written model that you have written yourself, or use a model from the library. Let's check the library. It's the same library as in Monolix. We have models for PK, PD, joint PK-PD, PK with double absorption, target mediated drug disposition, time to event, count, and tumor growth inhibition. I'm interested in PK-PD today, and actually I'm pretty lucky because the model I have estimated previously is available in the library. So for the administration, I will select a model which can support both extravascular and intravenous administration. I have no delay, one compartment, a linear elimination. For the response, I'm going to select a turnover model with production inhibition. The inhibition is full, meaning that the Imax parameter is actually equal to 1. And I have no sigmoidicity, so no gamma parameter. Then I have different parameterization, and I will select the first model from the list. And then I can see the model in the graphical user interface. It's described using this mlxtran language, and I'm going to explain exactly how it works on the slides. So I'm going to go back to the slides. And for the moment, we are focusing on the longitudinal section for the structural model. I have just copy-paste the model on the slides, and I will explain step by step. So first, we need the keyword longitudinal to say to Simulx that we are now defining the structural part of the model. And then we have a line input where I'm going to list all my individual parameters. Then I have a block PK, and in the block PK, I am allowed to use macros. Macros are actually functions, and we have different types of them. One that is pretty common, but that I have not used here, is the macro PK model. It allows you to define in one line typical PK models from 1 to 3 compartments. For example, I could write CC, that's going to be the name of my concentration, equals PK model, KAVCL. KAV and CL are recognized keywords, and Simulx will then transform this line into the analytical solution for a one compartment model with first order absorption. So this is very powerful, but the limitation is that you can use only one type of administration in combination with this PK model macro. In my case, I would like to be able to give both intravenous or oral doses. So instead, I'm going to use a combination of elementary macros that work like building blocks to build compartment models. So that's a piece of code I have here, and let's go line by line. So the first line is to define the central compartment. So I write compartment. I give this compartment a number 1. The volume, I will call it V, and the concentration, I call it CC. Then I can define the intravenous administrations, and I'm going to say they're going to arrive in compartment 1, so my central compartment. But not all doses will go via this route. Actually, only the doses that I'm going to tag in the graphical user interface with the ADM keywords equal to 1. So only doses with ADM equals 1 will go via this route. Then I'm going to define the oral doses using the oral macro. And this time, only the doses tagged with ADM equals 2 will go via this route. At the end, the dose arrives in the central compartment number 1, but not directly. Actually, it goes via a depot compartment and then transfers from the depot compartment into the central one with a parameter Ka that is indicated here. But I don't have to explicit the depot compartment. Actually, this single line is sufficient. And then I want to define the bioavailability, and I want to call it F. But actually, the keyword that is recognized by the oral macro is called P. So what I can do is to write the recognized keyword P equals F, which is the name of the bioavailability I want to use, and that I have put into here the input line. And finally, I can define the elimination. For this, I use the elimination macro. I eliminate from compartment 1 with clearance CL. And again, CL is a recognized keyword. So that's how I can combine these elementary macros to define this simple PK model with 2 different types of administrations. There is another macro that is used pretty frequently. It's a depot macro. It's a macro that you use in combination with ODEs, and that allows you to add the doses on one of your ODE variables. And this is done via the target argument. So for example, with this line, I would take all doses that have ADM equals 1 and add them on the ODE variable AD, which here, for example, represents the amount in the depot compartment. So that's what we can do in the PK block. Then I have an equation block. In the equation block, I can define ODEs or DDEs, delayed differential equations. We have 2 different types of solvers for ODEs. One is for non-stiff ODEs, and it's the one that will be used by default. If on the opposite, you want to use a solver for stiff ODEs, then you need to add this keyword into your model, ODE types equals stiff. In the model, everywhere I can have comment lines, and comment lines start with a semicolon. Then I need to define the starting point for my ODE integration. First, the starting time, and this is defined using t_0 equals the initial time here, 0. And also the initial value for the ODE variable. The ODE variables can have any name you want. So here I have called it R for response. So R_0 equals R0, and R0 is one of my input parameters. So that's for the initial condition. Then I can also have mathematical expression, like here parameter transformation. And for the time derivative, we use the syntax DDT_, the name of the variable, and just then the mathematical expression. Just remember that the power sign is a hat in the mlxtran syntax. And finally, I can have a block output where I list the model outputs. This line is especially important in Monolix. In Simulx, it's also mandatory, but what you put in this line is not so important because anyway, you will be able to output any variable of your model. So that's the key points I would like to mention for the model we will use. I have a few additional syntax rules that can be useful. First, the reserved keyword for time is T. So for example, if you want to define the time varying clearance, you can write it like this with a T keyword here. We also have keywords related to doses. So for example, the amount, time, or infusion duration of the last dose. So if I use, for example, AMT dose, the amount of the last dose, I can use it to define the dose-dependent bioavailability. So AMT dose always holds the amount of the last administrated dose, and that is pretty convenient in this case. And finally, you can also use if-else statements. Here, for example, I have a small example where I have a treatment that starts at time 0 and two different tumor size expressions before or after the start of the treatment. And I can put a condition on the time. All right, so these are the different rules to define the longitudinal block. So let me go back to the Simulx interface. So here I have the model as we have seen. And you remember that I said that actually what is of interest for us is the percent change from baseline for the response. And this is not yet defined in the model. So what I could do is to use here the additional lines to actually squeeze in some lines of code in this model without modifying the model file itself. So let's do this. I will call it response percent change. And this will be equal to the response divided by the baseline multiplied by 100, for instance. Can apply, and this is added to the model. So this is convenient when you want to do small changes where you can just squeeze in a few lines. If you want to do more larger changes, then you can open the model in the editor. If you click here, you will see the model in our MLX editor. Here you can write, modify, or write new models. And what is nice is this button here, that's a syntax checker. If you click here, it will check your syntax and raise errors that are meaningful if something is wrong. All right, so we have the model, and we can now proceed and define the other elements I need for a simulation. And all these parameters here at the top have been recognized as individual parameters. So what I can do next is to define the values for the individual parameters. I have an element that has been created by default, but for the moment, I just have values 1111 everywhere. So let me put in some values. And the values I'm going to put in actually corresponds to the values of the parameters for a typical individual as estimated during the modeling step. Okay, out 0.11 and IC50 35. All right, then I click OK. So I have some individual parameter values. Then I also need to define the treatment I want to give in. So let's click on the plus. And our goal is to simulate a multi-dose regimen with a loading dose. So I'm going to start with a loading dose. And you see here at the top, I have 3 different ways to define a treatment. I can either give a path to an external file, or I can define manually a few times and the amounts. So that's going to be convenient for the loading dose. So let me first give this element a name. So I will call it loading dose. The loading dose will be 200 milligrams. So let's put it in the title. You remember that in the model, we have 2 different routes, IV or oral. And actually, I would like the loading dose to be intravenous. So I will give it the ADM number 1. Then I want the loading dose to be at time 0 with an amount of 200 milligrams. And I also would like it to be an infusion, not just a bolus. So I'm going to add the infusion column, which is the infusion duration here. And for the duration, I want it to be 5 minutes, but actually the units of my PK parameters are in hours. So I need to be consistent. So these units here for the infusion duration needs to be hours. So that would be 0.83. So that's a pretty simple definition for a treatment. Actually, I could use more complex ones with having a cycle that I repeat or defining non-compliance, etc. But today I'm going to stay simple. So I click OK. That's a loading dose. And then I need to create another treatment element that will be 100 milligram once daily. That's going to be my once daily oral dose. For it to go through the oral macro of the model, I need to give it ADM number 2. And then I will use a regular scheme for it. It will start at time 24, because at time 0, I already have the loading dose. Every day, so every 24 hours, I will give 5 doses in total with an amount of 100. I click OK. So that's good for the treatment. Now let's check the outputs. I already have defined elements that are being defined automatically. Let's check what they are. So the first one just outputs the concentration CC on a regular time scale. This looks good, but I will go until 168 hours, which corresponds to 1 week. Then I have the response, but actually what I'm interested in is the percent change from baseline that I have defined in the model. So I will create a new output. And here I can select the response percent change from baseline. I'm going to call this regular ResPC. And again, it will go until 168 hours. All right. So now I have defined the base elements, and I will go to the exploration tab in order to set up a simulation using these base elements. In the exploration tab, I can have a really interactive simulation. On the panel here, I defined the elements I want to use. I'm going to use my individual parameters, and I will combine for the treatment the loading dose with the oral once daily doses, and I will output the regular CC, so the concentration, and the response percent change from baseline. I click apply, and I can see the simulation in the middle here. And then I can play with this simulation interactively by either modifying the parameter values or modifying the treatment. Before I start to modify things, I would like to freeze what I have on the screen. And to do this, I will click Add Reference. So that's the simulation we get if we give a 200 milligram loading dose followed by the 100 milligram oral doses. Let's check what is going on if we remove the loading dose. So to do this, I go to the loading dose definition, and I will set its amount to 0. And then I can go to the once daily dosing, and I will make it start at 0 with 6 doses in total. And we see that if I don't put the loading dose, then it takes much longer to reach the steady state. That's true for the concentration and also for the response. So that's a first insight, but for the moment, I have just defined a simulation for a single individual. What I would like to do next is to check what is going on for a population of individuals. To do this, I have 2 big options. The first one is to define a table of individual parameters. I can do this by going into the individual parameter tab, clicking plus, and here giving a path to an external table, which will contain the individual parameter values for several individuals. The file would look like this, for instance, with a column ID and 1 column per parameter. So that's one option. The second option is to do a Monte Carlo simulation. So this would mean that I will let Simulx sample individual parameters from a distribution that is characterized by the population parameters. To do this, I need to define the distribution of the parameters, and this will be done in an additional section of the mlxtran model. So I'm going to go back to the slides, and we're going to see how to define the parameter distributions in the individual section. I will first start with an example, with a simple example. Let's take a log normal distribution for the volume. Then the individual volumes are equals to a typical volume value VPOP times exponential the random effects eta. And the random effects follow a normal distribution with a standard deviation omega. If I want to write this using the mlxtran language, I will first start with an individual keyword to say I'm defining the parameter distribution, the inter-individual variability. Then in the input list, I list my population parameters, VPOP and omega V. Then I have a block definition where we define the distribution for the volume. The distribution is a log normal distribution with a typical value VPOP and a standard deviation of the random effects omega V. So that's the first example. Now let's see the general syntax. So in the general syntax, after the distribution argument, we can have different options here. So the first option is to have a normal distribution, then it would look like this. Or we can have a log normal distribution, as I had on the top. We can also have a logit normal distribution. It looks a bit ugly, the formula, but it's convenient because it allows you to have parameters that stay within bounds. By default, the bounds are 0 and 1. But if you add, in addition, a min and a max argument, you can actually extend it to any interval you want. And finally, we can also have a probit normal distribution, which is also bounded between 0 and 1. So that's the different types of distribution we can get. And then we need to indicate a location parameter. So the most common option is to use the keyword typical. So for example, typical equals VPOP. This gives a typical value of the distribution, which is the median. And the alternative is to use the keyword mean, and then you need to give the mean of the associated normal distribution. So if you have chosen a log normal distribution, this would be log of VPOP. It can be useful if you have, for example, estimated your model in Nonmem using mu referencing. Then you have directly estimated log of VPOP, and it can be convenient to use the mean argument here. And finally, we have a width argument. You can either give the standard deviation using SD or the variance using var. So that's always the standard deviation and variance of the random effects. And if you want no variability at all, then you can write no variability. So that's the different options we have to describe the inter-individual variability. So in my example, the full individual block would look like this. I have here the population parameters that describe the distributions. For all parameters, I have chosen a log normal distribution, except for the bioavailability F, which has a logit normal distribution to be between 0 and 1. And for IC50, I have set no inter-individual variability like this. For the moment, each parameter is independent from the others, but usually individuals which have a large volume also have a large clearance. So what I would like to define next are correlations between the random effects. The syntax to define correlations is to add in the definition block below the distribution definitions, this line, so correlation equals, and then for each pair of parameters that is correlated, you write R, and under parentheses, your two parameters equals the parameter representing the correlation that is also appearing here in the inputs. When you define these correlations, you need to have a correlation matrix that is block diagonal. So this means that you can have one or several correlation groups, but once you have a correlation group, all correlations must be defined. So if I have correlated V and CL, and then KA and CL, I also have to define the correlation between KA and V. This is mandatory. Afterwards, you can set this value to 0 if you want. And finally, so to have a block diagonal correlation matrix, every parameter can only belong to one of the correlation groups. So in this example, I have two correlation groups, one with V, CL, and KA, and the second one with R0 and K out. In Monolix, we use, and Simulx, we use correlations, but other software work with covariance matrices. So let me, all right, so I was a bit too fast. So that's a full model with the correlations. That's the same as I had before, except that I have this additional line and the additional correlations in the input. And now I would like to show you how to transfer your Nonmem model, where we generally defined a variance covariance matrix, into Simulx. So I have taken a simple model with KA-VCL following a log normal distribution. In the omega block, I have defined on one side eta Ka alone, and then a block for V and Cl, which here the covariance between V and Cl, and here the estimated parameters. In the mlxtran model, it would be convenient to use as inputs these estimated parameters here, such that they appear in the graphical user interface, and then it's easy to just copy the values from here to Simulx. So the first trick is that in the distributions of the parameters, for the typical value, you can directly use the estimated thetas. And then for the width, you can use the variance directly. Then you can directly give the here diagonal parameter values, so the etas 1, 2, and 3. However, for the correlation, you're going to need to add a bit of a calculation, and this can be done in the equation block. It's possible to calculate the correlation values from the covariances, and that's a formula to use. So if you write it like this, then what you're going to see in the graphical user interface are the parameters estimated from Nonmem, so it will be easy to type them in, and all the calculations are done directly in the model to give the correlation as requested by Simulx. All right, so let me go back to the Simulx graphical user interface. So now I'm going to load a new model that's going to have both the individual and the longitudinal block. You see that if I click on browse, it's going to tell me that all elements that I have already defined will be deleted. So actually what I'm going to do is to load a project that I have prepared in advance, such that I don't have to redefine everything. So in this project, I have the model with the individual block as we have seen on the slides, plus the same longitudinal block as before, except that I have here added directly in the model the line to calculate the response percent change from baseline. Then the outputs are exactly the same as before, and same for the treatments. They're exactly the same as before. What is new is that the parameters here of the individual inputs have been recognized as population parameters, so I can now define population parameters here. By default, I have just an object with values 1, 1, 1, 1. I don't want to type all the values one by one in the graphical user interface. So what I will do instead is to click on the plus to define a new population parameter element, and I will go via an external file. So I'm going to select a file where I have written the population parameter values, and actually this file looks like this. It just lists the population parameters and the values. And this element will be called pop external 1. And I can see that the values have been properly read. All right, so now I would like to define a Monte Carlo simulations with a population of individuals. So I will go to the simulation block. Here I will define how many individuals I want to simulate. So for example, 100. I need to define what are the parameters that I will use, and I will use the population parameters pop external 1, and then Simulx will sample from the distribution defined by these population parameters to generate individual parameter values. For the treatment, I combined again the loading dose with the oral doses. And as an output, I have, as before, the concentration and the percent change from baseline. Once this has been set up, I can click Run to run the simulation. And first, I see here in the graphical user interface the sampled individual parameter values. And in the plots, I can see the prediction for each individual, either as a spaghetti plot or as an prediction distribution, with the shades of blue being the different percentiles. And I have the same for the response. So that's nice, but you remember that actually we have found during the modeling that we had covariate effects on our parameters. So what I would like to do next is to add these covariate effects. This is done in the block individual and covariate. So here the rule is that the covariates must be declared both in the inputs of the covariate and of the individual section. So this is what I have done here. The parameters that appear only in the individual input will be recognized as population parameters, and those that appear in both will be recognized as covariates. Then you need to define and list the different categories of the categorical covariates. If you don't list any category, like for weight, it will be recognized as a continuous covariate. We can have any numerical value. And for sex and patient, I have listed the categories. So the syntax is the following: name of the covariate, type equals categorical, categories equals, and here you list the categories. It can be either integers or strings. If you use strings, if you use a space, you need to put quotes around the string. And however, special characters like percentage, etc., are forbidden. And this is done in both the covariate and the individual section. And then we need to define the covariate effects. And this is done in the equation block of the individual section. So here, let's first look at the continuous covariates. So I have defined a typical volume V tip that is equal to V pop multiplied by the covariate effect. The beta will be a population parameter that needs to appear in the input. And then this V tip, I use it here as typical value when I define the distribution. So I'm going to have a log normal distribution around V tip. So actually, I'm going to have this expression times exponential the random effects. And then for the categorical covariates, in this example, I have two different values for R0 for diseased and healthy individuals. And I can use an if statement, if else statement. So if patient is equals to mutation A or mutation B, I will use the R0 pop disease value and otherwise the healthy value. So this defines R0 typical, which I have used here. So that's a pretty convenient way to define the covariate effects. And the full model then looks like this. So I have added the listing of the covariate, weight and patient, the different categories for the patient, so healthy, mutation A or mutation B. And this is also done here. And then I have adapted a bit the population parameters and define the effect and use the typical values in the definition block. All right, so if I go back to Simulx, I'm going to do as before. I'm going to open a project that I have pre-prepared. In this project, the model is as I had on the slides with the section covariate, individual, and longitudinal. In this example, again, the outputs are as before, the treatments also. The population parameters, I have slightly edited them because now I have the two betas for the effect of weight on volume and clearance that are here, and the two different values for the R0 that are here. What is new is that these two parameters here, weight and patient, have been recognized as covariates, so I can now define covariates. I have a default element created, but it's a bit boring. It's just a single value. I will create a new element like this. And here again, I have two options. I can either give a path to an external file that would give the value of weight and patient type for several individuals, or I can define them using a distribution. So for the weight, I would like to sample it from a log normal distribution with a typical value of 70 kilogram and a standard deviation of 15%. And then for the patient type, I want to have half of the individuals that are healthy, 20% that have mutation B, and 30% that have mutation B. So I click OK. Now I can go back to the simulation tab. And here I'm going to adapt it slightly. So I have a large group size. I have the population parameters, the treatment as before, same outputs. And now for the covariates, I'm going to set this cov distrib1. So for each individual, we're going to sample a covariate value using the population parameters and the sampled random effect. We're going to generate individual parameter values that we can then use to simulate using this treatment and these outputs. If I run this, what we're going to see is that we have in the result tab all the individual parameters and covariates. So here I now have the covariates, and actually I have the table is pretty long. And in the plots we have, as before, the percentiles, etc. What I can show you here to prove that the covariates have been taken into account is to look at the response over time and actually to split by patient type. And then if I look at it like this, we clearly see that the baseline value is different for the patients having a mutation versus the healthy individuals. So that's a nice third step. But actually what we miss is that what we are doing for the moment is just to simulate smooth predictions. If we want to go one step further and simulate clinical trials, we're going to need to simulate measurements, so with residual error. So let's see how to do this. I'm going to again go back to the slides. And error models are defined in the longitudinal section. And I will start with a simple example first. For example, a proportional error model. So why my observations, either true observations or simulated ones, that are equal to the smooth prediction CC plus the residual error, that here is proportional to the concentration CC. B is the proportionality coefficient, and epsilon is just a standard normal random variable. That's one way of writing it. It's equivalent to this way of writing it. Maybe that's more familiar to you. If you want to write this using the mlxtran syntax, in the longitudinal section, we're going to add a definition block. And here we say that y going to follow a normal distribution around the prediction CC with an error model that is proportional. So that's just one example. Let's also check the general syntax. So again, X equals a distribution. I have several options for the distribution. The most common one is the normal distribution. So let's see how to combine it with different error models. We can have a constant error model, and it looks like this, or proportional as above. Combined one has both a constant and a proportional term. And combined two is the same, but relies on two different epsilons. So that's the different options for the error model. And then we can also choose different types of distributions. So if I look at the log normal distribution combined with the constant error model, then it would look like this, which is equivalent to this. And this is actually also called an exponential error model. And I can also have a logit normal distribution, which is convenient when you want to have your observations within two bounds. Here the bounds are small m and capital M, and the formulas look like this. So in my case, what I have done in the model is to add in the longitudinal block, in the longitudinal section, the definition block, with a normal distribution around CC and R. CC is with a proportional error model and R with a combined 2 error model. The error model parameters are added here to the input list, and the random variables that represent measurements with noise I called YCC and YR. Again, I go back to the Simulx graphical user interface and open a project that I have pre-prepared. And in this project, so in the model, it's as before with these 3 additional lines here at the bottom. Population parameters are as before, except that I have now the values for the error model parameters. Covariates are as before. For the treatment, I have the 2 first one as before, and I have added a third one that is just the oral doses, but starting from time 0. And in the outputs, in addition to the previous outputs, I have added 2 new ones. If we look at them, they output the variable YCC, so the prediction plus residual error on top. And because now I want to simulate a clinical trial, I would like to just have a few measurement times, as in a clinical trial. So actually, I have listed here the output times, have a few times after the first dose and after the last dose. And I have something similar for the response R. If I go to the simulation tab, this time I would like to simulate a clinical trial with 2 arms, one that have received the loading dose and then the regular doses, and the second one with just the regular doses. To do this, I'm going to create 2 different groups that represents the 2 different arms. Everything that is in shared applies to both groups. So for example, let's say I want to have 30 individuals per group. I will sample the individuals from the distribution defined by the population parameters. For the treatment, I need a different treatment in both groups. The first one is the loading dose plus what we had before, so the regular oral doses. And for the second one, I will have just the oral doses starting from time 0. For the outputs, I'm going to output the measured concentration with residual error, and same for the response, and sample the covariates from the covariate distributions. So now everything is set up for my clinical trial simulation, and I can click Run. And now I see the 2 different arms in the results and also in the plots. I have the 2 different groups. And you see that it's noisy. So that's the PK concentration, and that's the response. And actually, I can display it a bit differently. I can highlight just the dots that represent the measurement, and I can add a trend line. And here we see, so that's the 2 baseline pre-treatment measurements. And then when we add the treatment, it decreases. With the dosing time I have chosen in this example, I don't really see a difference between the 2 simulations group with and without the loading dose, but I could quantify this better by defining outcomes and endpoints. This will be the topic of another webinar. So for today, I would like to stop here with the graphical user interface. If I go back to the slides, so the key point when you start from scratch a Simulx project is to define the model using the mlxtran language. And this means that you need to define the longitudinal blocks. That's mandatory. You can have a block PK where you can use macros, equations for ODEs and DDEs, and definition to define random variables, for example, to define the error model. Then if you want to include inter-individual variability, you can add an individual block where you can define covariance effect in the equation section and parameter distribution in the definition block. And finally, if you want your covariates to be properly recognized as covariates, you need to declare them in the covariate block. So that's the structure of the mlxtran model. That's a key point. Once you have defined this, defining all other elements is really easy because you are really guided by the graphical user interface. Today, I have shown pretty simple examples, but it's possible to do also more complicated things. So in terms of models, we can have inter-occasion variability, time-varying covariates, more complex parameter distributions, and also define count categorical or time-to-event variables. For all this, I put here the links to the online documentation that explain you how to proceed. And also in terms of scenarios, it's possible to do more complicated things. So for example, your treatment can depend on covariates to do, for example, a weight-based dosing. You can compare outcomes in different populations, for example, with different sets of covariates. You can simulate clinical trials, check what is the impact of the number of patients or of different designs. As I said, you can really define outcome and endpoints to compare your different arms, do replicate and calculate the empirical power of your study, etc., etc. There are really a lot of options that we will present step by step in the feature of the week videos and in further webinars. With this, I would like to conclude and to open the Q&A session. So you can type your questions in the Q&A chat box and Pauline will read them loud.
Thank you very much, Geraldine, for this presentation. So we already have quite a lot of questions. First one, what is the easiest way to share the Simulx project, your Simulx project, with a collaborator who has their own license?
All right, so each time in the graphical user interface, I do a save. What's gonna be saved is actually the .smlx project. So this you need to send. Then all the external files you have imported into your SMLX project also needs to be sent. And then we have a result folder. In case you find that this is a too complex structure, it's also possible in the settings to actually, no, my bad, it's in the project settings. You can also save all your input user files into the result folder. Then you just need to send the .smlx file and the result folder together.
Thank you. Next one, what about the speed of the simulations? For example, is it comparable to mlxtran?
So Simulx is very fast because all the calculations are done in C++. So I have not done a side-by-side comparison, but I expect it to be at least as fast as mlxsolve or even faster.
Okay, thank you. Is it possible to write an output equation in mlxtran that tells the time of the Cmax?
Time of Cmax is possible, but not super straightforward. We have examples online about how to do it. One option is to put it in the model file, but actually you can also use these outcomes to post-process. So here, that's a bit advanced, but let's show it quickly. You can here select your output CC concentration and then say you want to take the maximum for each individual, so the Cmax. And here you can select time of Cmax. And then for each individual, you're going to have a table of the time of the Cmax.
Okay, thank you. Can we perform trial simulations in Simulx accounting for dropout?
So not fully in Simulx. So you would do your simulation in Simulx. You could have a time to event model that simulates the time of the dropout, but then you would need to post-process your results elsewhere, for example, in R, to delete all your PD measurements that are after the dropout. So it's not fully GUI-based, but it would require a bit of post-processing afterwards.
All right. You have shown how to define a distribution for the weight. Is it possible to also set mean and max values in addition?
So if you want to set mean and max values, you need to use a logit distribution. If you have a logit distribution, then you can put your lower and upper limit. But by definition, a log normal distribution spans between 0 and plus infinity.
Okay. Is there a way to include both inter-individual variability and uncertainty on the parameter estimates in the simulation?
Again, not directly. So it needs to be in two parts, basically to include the uncertainty of the population parameters. You would do this outside of Simulx, and we will provide soon our package to help you for this. You would generate different sets of population parameters that account for the uncertainty on the population parameters. And then in the population parameter tab, you would here load an external file that accounts for the uncertainty on the population parameters. And for the inter-individual variability, you do it as usually. If you don't like the external file, you can also here define a distribution for each of your population parameters, but that would be a diagonal uncertainty matrix, basically.
All right. Someone asked what would be the difference in simulating a group with 10 individuals and 10 groups with 10 groups with 10 individuals and 10 replicates, and 100 group and 100 groups. What is the difference between simulating different groups and groups with replicates?
So at the end, you have the same total number of individuals, but the way the results are presented is a bit different. Basically, especially when you define outcomes and endpoints, they are calculated for each group and each replicate. And then if you do several replicates, you're going to see what is your endpoint over which replicates, and you can do statistics. So basically, having replicates really allows you to simulate a clinical trial with a like realistic number of individuals, and then check what would be the variability from one trial to another one. So that's really in the perspective of estimating empirical power for a clinical trial. On the opposite, if you are just interested in comparing two treatments on a large number of individuals, then do just one replicate and put a large number of individuals to compare what is going on. And we also have this option here at the top, same individuals among groups. If you want to be sure that the difference you see between the two groups is due only to the treatment and not to the fact that you have different individuals, you can enforce the individuals to be the same in both groups.
Okay, thank you very much. I think we have to stop here. We still have a few questions, but I will answer them in the chat if people want to stay connected just to see the answer.
All right. So thank you very much for the questions. And so the recording will be online before the end of the week, together with a small case study showing this small story. Have a nice day. Bye-bye.
Thank you, everyone. Have a nice day.